As of 2024, over 4,000 lap engines have been ordered, making it the fastest-selling jet engine in aviation history. Each of the 18,000 parts entering this assembly line is laser scanned and verified against a digital twin before it can proceed.
The coordinate measuring machine used in this inspection is accurate to 1.9 microns, roughly 1/50 the thickness of a human hair.
The Durham campus operates without traditional management hierarchy. Every technician on this floor is certified to build an entire engine from start to finish. This forging will lose 60% of its mass during machining, and the final disc geometry is hidden inside the metal, waiting to be revealed.
The carbon fiber in this room began as polyacrylonitrile precursor in Japan.
Once the epoxy surfaces touch, the bond is instantaneous and permanent. There is no repositioning, no second chance. At full vacuum, this bag applies 10 tons of atmospheric pressure across the laminate, the equivalent of stacking 3 pickup trucks on top of this single fan blade.
For 4 hours at 177 degrees Celsius, the epoxy molecules cross-link into a permanent thermoset matrix play-in, a transformation that cannot be undone.
The blade emerging from this mold has the same structural architecture as a dragonfly wing, stiff and trellis. The ultrasonic inspection reveals every layer within this blade. 20 plies, each a 1/4 millimeter thick. The diamond coating on this cutting tool is extremely thin, yet it will machine hundreds of blades before requiring replacement. This blade will be measured at 384 points porteds, and every single one must fall within a tolerance band half the width of a human hair. Each of these blades contains 200 laser-drilled cooling holes, each hole smaller than the diameter of a human hair, each drilled in under 1 second. The human eye, aided by ultraviolet light, can detect a crack 1/10 the width of a human hair, but only if the inspector never blinks at the wrong moment. The plasma jet reaches 12,000 degrees Celsius, hot enough to melt ceramic powder in flight and deposit it as a thermal barrier 200 microns thick.
The cobalt blue color comes from the
200 holes, each drilled by a laser pulse lasting 1/trillionth of a second, cold enough to leave the surrounding ceramic untouched.
The internal lattice structure of this fuel nozzle was not designed by a human.
Nodules. Each powder particle is a perfect sphere between 15 and 45 microns. Produced in Sweden.
19 hours of continuous laser fusion have produced 19 fuel nozzle tips, each one containing internal geometries that no drill or casting could ever create. The parts have been stress-relieved and are now being separated from their supports as the manufacturing sequence progresses to post-processing. The abrasive media flows through passages the width of a pencil lead, polishing surfaces that no tool can reach and no camera can see.
This single nozzle will spray fuel into a flame front traveling at 30 meters per second, and it must do so identically. In this room, a single speck of dust larger than 5 microns could score a bearing surface and reduce the engine's life by 10,000 hours.
Each disc must be aligned to within half the thickness of a sheet of paper before its splines will engage. Force is never used, only alignment.
The final balance is accurate to 0.5 gram/centimeter so, the equivalent of a paper clip placed at the rim of the disc, spinning at 12,000 RPM. The welds on this combustion liner must withstand 1,700 degrees Celsius, a temperature that would melt the Inconel itself if not for the cool. Each of the 19 fuel nozzles is torqued to the same specification, in the same sequence, with the same tool. Variation is the enemy of combustion stability. All fuel nozzles must deliver fuel within a very tight tolerance of each other. Any significant imbalance would create a hotspot in the combustion chamber that could damage the turbine. The turbine blades must be centered within 1/10 of a millimeter of the combustion chamber exit. Every blade is weighed to 1/100th of a gram, the weight of a single grain of rice, and paired with its opposite number to cancel all rotating forces. The fir tree root design distributes 12 tons of centrifugal force across 6 contact faces, 3 on each side. At operating speed, these blades will grow outward by 0.5 millimeter straights. The cold clearance measured today must predict the hot geometries. The modules converging on this stand were manufactured in France, India, Thailand, and across the United States. Every safety wire is installed by hand, in a specific direction, to a specific twist density, a skill that has not changed. The fire is now contained loose. Combustion gases at 1700 degrees will travel from this chamber through the turbine in less than 3,000ths of a second. The core engine is now complete. Every bolted flange, every spigot, every safety wire installed and verified. A single assembly of 4 modules weighing 3 tons.
Each of the 18 fan blades weighs just under 5 kilograms at produce. But at takeoff thrust, the spinner must be concentric to within half the thickness of a human hair. Any eccentricity would disturb the airflow into the fan and cost 1% in fuel efficiency.
The 18 blades on this fan are now balanced to less than 4 gram centimeters, the equivalent of a postage stamp at the blade tip, spinning at 2400 RPM. Engines. Guided by 4 technicians and a crane operator, the 2-meter fan module is mated to the core engine, a fit measured in microns.
When complete, this engine will contain over 200 external tubes and harnesses, a circulatory system carrying fuel.
The accessory gearbox takes 10,000 horsepower from the engine's high-pressure shaft and distributes it to the aircraft's electrical, hydraulic, and fuel systems.
At takeoff power, this generator produces enough electricity to power 70 average homes, and it must maintain exactly.
Over 500 inspection points must be verified and signed off before this engine is cleared for its first run. Every item in a decision.
The engine has traveled 800 meters from assembly bay to test cell, but the journey from raw material to this trailer has covered.
The test cell fuel system will deliver up to 8,000 liters of Jet A per hour at takeoff power. A river of fuel flows.
Starting engine SN LEAP 4427, test sequence 001, all systems nominal, commencing start.
At 28,000 pounds of thrust, enough to lift a fully loaded Boeing 737 MAX off the runway in under 30 seconds, sustained for hours at 40,000 feet. At 2,000 frames per second, the flame kernel that ignites this engine is visible for 6 seconds TARS.
After every acceptance test, selected hardware is removed and inspected. The engine must prove not only that it can perform, but that it can survive its own performance.
At 500 times magnification, the surface reveals its secrets. Every melt pool from the laser, every polishing mark, the engine has been disassembled, inspected, and reassembled times. Every component that was removed has been proven worthy of flight and returned to its place. The film wrapping this engine emits a vapor that will prevent corrosion for an extended period, long enough to cross. Valued at approximately $14 million, this engine will travel by truck and aircraft to Renton, Washington, where it will be installed on a Boeing.
The engine will travel over 4,000 kilometers pointed by truck and by cargo aircraft wanted to reach the Boeing assembly line where its airframe has been waiting. After 4,000 kilometers, the engine arrives at the largest building in the world by volume, the Boeing Renton factory, where 42 737
forward mount torqued, aft mount torqued.
The engine is now mated to its aircraft, the 2 largest assemblies of the Boeing 737.
Within 72 hours of this moment, this aircraft take off from Renton Field on its first flight.
And in a few hours, this aircraft will take off on its delivery flight, and for the next 30 years, its 2 LAP 1B engines will carry it across the world.
Starting number 1.
The start sequence that began with a single spark in the combustion chamber now repeats on the wing.
Number 1, stable.
At 140 knots, the captain rotates, and 56,000 pounds of thrust lifts 80 tons of aircraft. At 35,000 feet, each engine consumes just 1 gallon of fuel per second, propelling 200 passengers forward at 85% of the speed of sound.
I've been building engines here for 22 years, and this little part right here, this is the one that still amazes me.
The CFM International LEAP 1B turbofan jet engine PEST, 8,000 components, 40,000 orders, 1 standard, absolute perfection. Each carbon filament in this blade is 7 microns in diameter, 1/10 the thickness of a human hair, and there are 54,000 of them in every square centimeter. Cobalt blue ceramic, 187 microns thick, pierced by 200 laser-drilled holes. Smooey, the armor that allows this blade to survive breeds. Inside this chamber, 19 fuel nozzles, each designed by artificial intelligence, will spray fuel into a flame front. This is how the world flies.